The word drug can spark up many emotions. It can make you feel thankful because they have helped you or a loved one in the past. They can make you feel angry because someone you have known had a drug addiction. You may even feel reluctance in trying to take a medication and fear of the side effects. In Chapter 10, we will be discussing pharmaceuticals. We will talk about how dependent we are becoming of prescription drugs, the harm of illicit drugs, herbal remedies, and how drugs are designed. One old home remedy from the ancient Greece was from Hippocrates. He would advise the boiling of willow bark to help with a fever. The classic white willow tree, Salix alba, provides more than just shade and shelter for nature's animals. Salicin is a key ingredient that is isolated from the tree and converted into one of the most reliable and heavily used drugs, aspirin. It's used as a fever reducer and a pain reliever and as an anti-inflammatory agent. When scientists tried to determine the reason for reducing the fever, they were able to separate components from the tea made from the bark. They found that one of the components did indeed reduce fever and inflammation. However, it also produced several side effects, such as heartburn, nausea, a rash, and a shortness of breath. We have been discussing carbon throughout the semester. This is because all living things consist of carbon. Carbon is so important they've actually dedicated an entire field of study to it, called organic chemistry. There are over 12 million known organic compounds of the 27 million compounds total. So almost half the compounds we know of are organic or contain carbon. Why is carbon so remarkable? It has the ability to make very strong bonds in multiple ways. If you look at the periodic table, it's in the 4th row. It also means that it has 4 valence electrons, which means it can make 4 different bonds. Typically, they would look like 4 single bonds, maybe a double bond and 2 single bonds, a triple bond and a single bond, or maybe even 2 double bonds. Organic chemists usually focus on carbon with a small group of elements that are usually bonded to it, like oxygen or nitrogen. There are several different ways to depict compounds. Let's take a look at butane. The chemical formula of butane is C4H10. The chemical formula simply states the element and the quantity of each element. The structural formula, which is here, indicates the atoms and their arrangement with respect to one another. So you notice that there's carbon with 2 hydrogens off of it and then bonded to 2 other carbons. And then that carbon has 2 other hydrogens with 2 other carbons. And then this carbon has 3 hydrogens. The condensed formula takes the structural formula and shortens it down. It tries to inform the reader what things are bonded to what, but the reader will need a little bit of chemical background to truly understand it. For instance, the reader will need to know that carbon has 4 bonds while oxygen only has 2. So a condensed formula for this one would be CH3, because there's a carbon with 3 hydrogens, CH2, because this first carbon is bonded to another carbon with two other hydrogens, CH2, because this carbon is bonded to this carbon and two other hydrogens, and then CH3. The ball and stick formula attempts to show it in a three-dimensional pattern. For instance, this one looks like it's going back, this one looks like it's coming out. The space-filling model tries to depict the structure more accurately, saying that these are not actual sticks. There's no space between them. Now let's take another look at these pictures. Take a minute to count the number of carbons and hydrogens in these two pictures. Notice that they both have 4 carbons and 10 hydrogens. However, they do not look the same. These are called isomers. Isomers are 2 or more molecules that have the same chemical formula, so they're both C4H10, but different structures and properties. They may have the same elements, but because they're arranged differently, they do not behave the same. One way, the most common way, to depict organic structures is with something called the line drawings. The method is much easier for chemists, but once again, the reader must have a little bit of chemical background knowledge to understand what it says. For instance, it's assumed that every carbon has 4 bonds. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. At each of the bend in the end of the line, it is assumed that there's a carbon. So notice carbons are here. It has the same general shape. Unless it's depicted otherwise by putting a different chemical abbreviation at the end. Hydrogen atoms are left out of the picture when they are bonded to carbons because they're too cluttered. Then you combine this information to read the structure. So you notice that the bottom structure looks like a pentagon. While at each bend, there is a carbon atom. There are 2 lines coming off each of the bends. This is indicating 2 bonds to 2 other carbons. Since each carbon has 4 bonds, there are 2 hydrogen atoms that are there, but are not drawn in. It just makes it look cleaner. Let's break down the line angle drawing. The chemical formula states the number of carbons and hydrogens. The structural formula shows the bonds of the compound. So it shows what everything is bonded to. The hydrogens are removed for the line drawing. So notice 1, 2, 3, 4, 1, 2, 3, 4. Also notice that the first 2 are isomers because they're the same chemical formula and different arrangement. They're both C4H10, but they have a different number of but they look differently. One is just straight across, the other one looks almost like a Mercedes sign. The next 2 are not isomers because the chemical formula are not the same. One has 14 hydrogens while the other one has 12 hydrogens. Another structure we will discuss is benzene. Benzene is extremely stable. Benzene is an extremely stable arrangement that is used often in organic chemistry and an important part of many drug molecules. It is part of another compound, which is also called the phenyl group. In the first picture, you can see the atoms drawn, including the hydrogens. Notice the double single bonds, the hydrogens coming off of it. The next picture, the hydrogens are not drawn. It is assumed that the reader knows that they are there. They did not vanish, they are simply assumed. Notice in both of these first two pictures, double and single bonds are alternating. But in the third picture, it's a circle. Well, when scientists had better technology, they started to explore the benzene molecule a little more. They realized that the bonds between the carbons and carbon atoms were not actually double and single, but spread evenly throughout the compound. This is the more accurate viewpoint. We begin discussing functional groups in Chapter 9. These are distinctive arrangements of groups of atoms that impart characteristic physical and chemical properties to the molecules that contain them. These are so important in the reactivity of a compound that chemists focus on them when they're studying a compound. They often simplify the entire compound by indicating the functional group and attaching an R group. So they would put an R group right here. They put an R group right here to the remainder of the compounds, which would be any amount of carbon atoms. The first functional group on this list is alcohol. It would be abbreviated ROH. Methanol is the most simple form of alcohol, which is made of degrading of wood. Ethanol has 2 carbons, and this is the fermentation of grains and sugar. This is just one example of a functional group. Essentially, these are what predicts the chemical's reactivity. Carboxylic acid is another really common functional group. It is commonly written as COOH. To indicate carbon-oxygen double bond with an OH group. This reacts like an acid by donating a hydrogen of the OH group. As we discussed earlier in the semester, an acid is a compound that donates hydrogen. The aspirin compound contains 3 functional groups. It contains a benzene ring. Its presence makes it possible for the fatty compounds and cells membrane components. Carboxylic acid and an ester. Felix Hoffmann, the chemist who invented aspirin, reacted salicylic acid with acetic acid to create an ester. So here's the ester. Ester functional groups are often found in drugs, flavorings, and fragrances. So although some of the negative side effects from the willow bark are still there because of the acid portion of the compound, the ester gives it a bit better flavor and less irritating on the stomach lining. Once the aspirin is digested and reaches the site of its action, the reaction is reversed and the ester is broken down again. The salicylic acid is what is giving the aspirin the fever and pain reducing properties. So this bond ends up breaking, and this acid part here is what's doing all the work. You will notice that these 3 pain relievers have very similar functional groups. They all have benzene rings. 2 of them have carboxylic acids. The similarity in structures explain why they perform similar tasks. Functional groups may impart a polar aspect to the molecule. A polar molecule has partially charged separation. Remember we talked about partially negative and partially positive before when we talked about hydrogen bonding. Positive and negative charges interact with one another. This includes partially positive and negative charges. This is why water is such a good solvent. It has partially positive and negative parts of the molecule that can interact with so many other molecules. The functional group provides a positive and negative area on a molecule that ordinarily would not have one. This allows the molecule to react more readily. Without a functional group, the molecule did not have any area with any kind of charge. The drugs would they would only be able to dissolve in fat and not in our cells. Sometimes it is even better to have complete positive and negative charges rather than just partial. For instance, with this example, the nitrogen is a positive charge and the chlorine is a negative charge. There are no partial signs here as there were at the previous slide. The salt forms a drug that are often preferred because they're more soluble in water. They have no odor and have higher melting points, which makes them have a longer shelf life. Let's explore aspirin a little bit more and determine how exactly it works. In order for your body to communicate internally, chemical messages are sent throughout the bloodstream. Hormones are chemical messengers produced by the body's endocrine glands. Hormones encompass a wide range of functions and are similarly wide range of chemical composition and structure. Enzymes are proteins that act as biochemical catalysts, influencing the rate of chemical reactions. It speeds up the reactions and makes them actually occur. Aspirin works by inhibiting the production of certain enzymes responsible for producing specific hormones. Aspirin and other drugs are physiologically active, but not anti-infectious agents, are almost always involved in altering the chemical communication system in the body. Aspirin, as well as non-steroidal anti-inflammatory drugs, or NSAID, work by inhibiting the catalytic activity of certain enzymes. The mode of action is due to the ability of aspirin to block the action of cyclooxygenase, or COX-1 and COX-2 enzymes, from producing the hormonal compounds prostaglandins. Certain prostaglandins are responsible for the body's response to pain, inflammation, and fever. Prostaglandins cause a variety of effects. They produce fever and swelling, increase sensitivity to pain receptors, inhibit blood vessel dilation, regulate production of acid and mucus in the stomach, and assist kidney functions. By preventing COX-2 enzymes from catalyzing prostaglandin production, aspirin reduces fever and swelling. It also suppresses pain receptors and so functions as a painkiller. So it doesn't actually relieve any of the actual strain, it's just blocking the chemicals from telling your brain that there's an issue. But the drug, as do the NSAIDs, also inhibit COX-1 enzymes that primarily make hormones to maintain proper kidney function and keep the stomach lining intact. That's why they say to limit your amount of anti-inflammatories, because they can actually harm your kidneys. Thus, NSAIDs are not sufficiently selective to affect COX-2 without shutting down COX-1 as well. Researchers raced to create nearly a dozen new candidate drugs to block COX-2 alone. This work resulted in an emergence of new class of medicines in the late 90s called COX-2 inhibitors. Two widely popular and heavily prescribed COX-2 inhibitors are Vioxx and Celebrex. These new super aspirins were touted as being safer and more effective than currently available NSAIDs. The premise is that since they do not act on COX-1 enzymes, they should have fewer gastrointestinal side effects. The reality is that they have not been proven to be more effective or safer than aspirin or ibuprofen. In fact, they have been proven to be more dangerous than helpful. Uncertain future for the COX-2 inhibitors is due to the emerging evidence of the questionable safety. As of 2008, they have been pulled off the shelf by the manufacturers. This is the end of the first part of Chapter 10. The next part is going to continue this conversation on how the exact chemistry of drugs can affect our body, as well as the natural remedies.